have had in the audience, I want to offer something for the students, okay, especially the very young ones, both in prefer algebra and in, say, beginning differential geometry. Examples, I'm going to do rotations. Probably you're familiar with what the Euler angles, have you seen them in school? Euler angles, rotation of frames. Okay, better if you haven't seen them. You have seen them. So they are very unnecessary and advanced mathematics. I also solve that the system, the equations of the structure for a manifold defined only by the metric without a connection, without a comparison of vectors of the distance. Of course, in the metric we can canonically derive a comparison of vectors of the distance, which is what the Chile and was called almost at the same time. So, since it is more algebra, actually prefer algebra, it appears as very complicated. In reality, the other day in the first time I spoke, it is almost trivial. I don't study papers on prefer algebra, ask me a question, and I do the computation from a few basic things. Okay, let me do rotations. Well, first of all, a rotation we learn in high school, or we should have learned in high school, that the product of two reflections in the plane is a rotation, whose angle is double the angle made by the two lines which are reflected. So, I'm going to do some unit vectors. Why? Because they are not unique. I just start the scale factor and I put it at the end. So, I'm going to reflect T, with respect to the line with the unit vector T, I'm integrating the plane. If I have U and U prime, the reflected one, and look, this is that rotated. So there, why? Because T U prime is equal, obviously, the sine, the cosine, everything is equal to U2. Hence, the inverse of T is itself.
But you write, U is a vector.
Yes,
and T is an operation. U is a vector.
Yeah, U is a unit vector, T is a unit vector.
U is a vector. And T is an operation.
Okay, you can use different ways as operations. Let me just.
But then it is an operation. You cannot write T on the right.
Yeah, so if this is a reflection, then T is another vector.
Okay. They don't say that. He said it was a rotation.
The rotation is like composition of reflection.
But the product of two vectors is principally not
It is a vector. You get the complex number.
So there is already a lot of going on in this way of saying.
So,
I understand.
since a rotation is a product of two rotations, I perform now the two reflections. I perform the second reflection. Now on the prime, and therefore because this one is a 1, so I have now up to the second rotation. Now on the line T2, unit vector then this is going to be U, T1, now the second rotation, T2, and here I'm going to have T1, T2 to 9. Now what is this? That is a rotation. You don't identify it, but that is a rotation. Okay. What is T1, T2? It is an exponential. Okay, how? Well said, because T1, T2. Before product is T1, T2. Stereo plus T1 dot T2. This is the cosine of the angle that T1 and T2 form. And this is simply I tan the covering I. If those two are unit vectors, nevertheless, they are going to make an angle. And this is going to be, you will see quite immediately, 64. If I think this is a bivector, but it is not a unit bivector because the two vectors are forming a number different from pi over 2. So I can write this as something which happens to be the sine of phi T1 and A1, A2, where A1 and A2 are orthonormal. And that is the exponential n to the phi A1, A2. Now, it is easier to go that way, because if you perform the power expansion of that, when you have this, it's as if you have the unit imaginary, and you have Euler's formula. Okay? So it is easier to go that way. And multiply. Okay.
Sorry, Jose.
Yes.
There is a small misleading. If we write the stereo product of A1 and A2, then the sign, no, then the sign is included in the stereo product. So it's the second line is this is the sign is inside here.
Yes.
So the right thing is to write.
Okay, you take the same orientation, that's clear.
No, but this is not the right thing.
It is not normal.
Right, here, the norms.
I am not with norms. I will have to put norms. Okay.
Anyway,
No, there is an easy way of doing norms which only Keller does. Okay, we have said the norm of A1, A2, A3, and make it 25 more, and you multiply that by itself, it is identical, so you are going to have a scalar part. The problem is, you have to be transforming A1, A2, etc. So that will happen. What did Keller do? And he invented what he called scalar products. And he used that for certain purposes. We can see that if we have time this afternoon, we will learn tomorrow. Well, he reversed the order of all those. And if you reverse the order, now you are going to have, etc. So this is going to go out with this is going to go out with this. And if you have an exterior product, okay, of unit vectors orthonormal, the norm comes automatically. And if they are not orthonormal, you put the factors at the front, okay, and all this experience, and books on Greek for algebra make a mess, and books on whatever consider matter. Okay, so we have reached that. This is for T1, T2. What is going to be T1, T2 to the minus 1? It is going to be e to the minus phi A1, A2, U, the vector E to the 5, E1, E2. Now we are going to consider rotations. That is a rotation, but we are going to connect with what? You read about rotations in the literature. First of all, we have to distinguish between, are we talking about the rotation in a Euclidean vector space or in a Euclidean space? In the Euclidean vector space, we have only one Euclidean space. Okay, the vector space, only one vector space. If we have a Euclidean space, at each point we have a vector space. So, we have to be careful when speaking about rotation. That is the first thing to be clear when we are doing, if I have to solve a problem of rotations. Second, am I talking about the rotations from one vector to another, and there are many, or am I talking about the rotation of one place from one basis to another? Third, still another one, which is, are we in dimension 2, in dimension 3, in dimension 27? If we look at things from the perspective of quaternions, there is a relevant number there, number 3, which are the 3 units imaginary that Hamilton found. But if we look at it from the perspective of Clifford algebra, that algebra is isomorphic to the Clifford algebra of Euclidean space, vector space of dimension 2. So we have 2, 3, and when we talk about rotations in 3 dimensions, that is nonsense. Rotations are in 2 dimensions, and the 3 dimensions come from somewhere else. If we follow the Euler numbers, okay, we have 3 Euler numbers to describe the problem. So if I were in dimension 27, how many Euler numbers there are? The problem is that when rotations happen, okay, not around an axis, but in a given plane, which in 3 dimensions is the plane perpendicular to the given axis. So, to say rotations around, if you give us an example when you teach rotations around a given axis, you should say, in 3 dimensions, okay, we have this axis, and we are going to consider rotations about this axis. So, for instance, that problem, how does it fit in here? Well, the axis of rotation is going to be, okay, perpendicular to this vector. So here, instead of A1 to 2, we introduce, if you wish, an A3. But A1 and 2 is not A3. A1 and 2 is equal. A1 and 2 is equals to A1, A2, A3, A3. Because A3 is 1. These have the properties of the unit imaginary. It is of a square minus 1. And when you want to go from vectors to the plane perpendicular to them, you multiply by this angle or square. Okay? So, what will happen with hence we so let's go then to rotations. In a vector space, okay, rotations happen in a given plane. In a finite space, they happen in all that plane and all the planes parallel to it. What about we say in 3 dimensions, and this is only for 3 dimensions, we can write this in terms of the perpendicular direction, but not in 87 dimensions. Therefore, the important number of rotations is not in 8 dimensions, so it's neither 2, neither 3, nor n. The important number is 2, because rotations happen in planes. And two vectors define a plane independently of whether that plane is embedded in a space of higher dimension. Questions, please.
Actually, it's more than a remark.
Please speak up loud and increasing.
Just a quick remark. It's no doubt this is much better than talking about axis of rotation because it's not.
And whatever is in my opinion, go ahead.
Okay, I have that is an example. Anyway, when we talk about higher dimensions, we still need to take into account that not every rotation happens in a plane.
What?
Yeah, true.
Okay, where does it happen in rotation? Do we be then talking about some transformation which depends on more than one parameter?
No.
Okay, show us.
Okay, what do you mean by more than one parameter?
One.
Yes, we have more parameters. Yeah, of course.
And first is elementary, which is in terms of one parameter.
If you restrict to one parameter, then you have a flow
In dimension 4, when I take two orthogonal planes, and in one rotation of say some angle,
Doesn't have to be other.
and another rotation of another angle.
Yes.
Is this a rotation? This whole thing?
Okay, that is the composition of rotation.
It's not a rotation.
Oh, call it what I want. I don't care about names. I always have problems with you and names are concerned.
You have stated the basic question, but if both planes are we are not
Well, it's here called
it's a question of subalgebra. If we are working with planes that form a subalgebra quaternions, then the result is always another rotation. If we are working in a hyperbolic plane, and all are of this kind, we also have a hyperbolic. But it is a question of subalgebra. Sometimes this combination can be a pure.
I suggest that those questions that have to do with you, he, I, we need for us to handle. But now we let the students ask the questions that concern them.
No, but this is very important to make.
All of us believe that what we do is the most important thing in the world. He does that, you do that, I do that.
What is try to understand?
Oh, no, okay. The transformation that you know involves two parameters. A rotation in one plane and a rotation in the other
And
plane.
more simply, this composition of rotation, is this still called rotation?
Well, I don't use names, because when I use names...
Talk about rotation, so you tell me what is rotation.
One parameter rotation. Because when we do...
One parameter. This I turn alpha and this I turn 2 alpha. So I have only one parameter.
Yes, but then you are a special case of the product of two elementary rotations.
But it's only one parameter.
Yes, but the fact that you reduce these two, okay, depends, it is like a symmetrical tensor.
Sorry, but if there's a rotation group.
You have my point is, the point I made from the very beginning is that the question that we ask ourselves in software depends on where you read. And in one case they are doing rotations in a vector space, in another case they are doing it in a vector space or in a Euclidean space. In other cases they are thinking of the rotation of the vector, determined by a pair vector. And the pair vector do not determine a rotation, they determine one family, one parameter family.
There's a big difference between reading books and listening to a talk. If I read books, very often it happens that the author of the book died already.
Yes, my point is to collect, okay, what is the essential thing, okay, in the discussion of this author? What is the essential thing in the discussion of that author? One day in school, somebody had to present, okay, something about the behavior of the when Don Quixote, with his spear, was going to find a lion. He opened the box of the jail of the lion and was going to. And the teacher told us, okay, you write something about it. He liked mine, okay, and I was chosen to do it. So I asked a few people, and I saw that different people had different things in mind. So I tried to put all of them together. So the aspects of touch, I asked myself at one time, okay, or incidentally, if you want to say, how does this connect, okay, with the Euler angles? The Euler angles are going to be in that. If I use a basis, and so far I haven't talked about basis, then the Euler angle comes in how the dual vector of this vector is represented in some other frame that I have chosen ab initio. But if I get rid of that additional frame that I have chosen ab initio, which is unnecessary, now what does this rotate? This rotates a vector. What is a frame? It's three vectors, three dimensions. What is a frame? Three vectors. Okay, where are they? Those play the roles of the argument. Okay? But this is not of the essence, because it depends on what frame I want to represent, use to represent. Now, you choose the notation, and I said, you choose or decide where the result I obtain will come from what I don't know which one we're talking about. Okay? And the what topological conditions or properties is no worth. That is not my problem, because if I did that, I would do financial physics. And the world is waiting for me to do financial physics. All right. Now, if you wish, later, if you have still, in view of this, if you have questions, please, students, write them up. Okay? Then, you can take the opportunity, then I'll answer. I will do a little bit more of triple algebra, things like the following. Triple algebra, when you get rid of all those complicated, an anecdote from last year. I had the product, scalar product of two multivectors. I said, so you students may be interested in this. Okay, because as soon as you start to decompose the different products, and you think sometimes yes, sometimes no, and so on, you might face things like that. And understand, and you were surprised. Oh, this is new. Obviously, I got into thinking overnight that I thought I was doing system also. Okay? And I gave credit to estimates. So, two big professors that were at Alternate last year, they said, oh no! And how does one do that? I told them it. And then, a professor like Ernesto eventually told me, oh, if you take this on such page from Ernesto, and you combine with this comment, and with that theorem and so on, yes, this is obvious. Because it has to be etc. all the way until, okay, we run out of factors in there. Why? Because if it is not that way, you don't reach R minus S. from more sophisticated perspective, then the simple problems. But what's the problem that this you cannot see what he was writing because you must. Oh, it's too light. You must take another. Yeah, thank you. Sorry. Yes, now I have. I apologize. So I have here. Is that the problem? Is that the problem? Okay, A1 on the way to AR, B1 on the way to BS, and here AR, this parenthesis is this, and here A R minus 1, here A R minus 2, etc., and assuming that. And assuming that R is smaller than X, you get that. If R is greater than I would do it this way. 1 by 1 is multiplying that, and that multiplying that, etc., etc. This is something practical for you who may have to compute with. Okay, if there are no questions from students, okay, then I'll go to the next topic, which is the solving the system that we had yesterday. If I'm given a quadratic symmetric differential form, that defines uniquely some a set of omega rings. I assume positive derivative, one can change that, it's very easy. Such that this is satisfied and the omega rings are going to be functions of the dx's, of the x's, and some additional coordinates which are important. And
the form was positive and on the left was positive.
Yeah, positive left. Yeah. If not, I will introduce here an epsilon which is 4.1. Okay. And now the following system.
But this is not a unique way. There are many ways of.
Yes! Okay, this is why I introduce these to represent other ways. And that made a case of 2 dimensions where the group is the group of orthonormal matrices. Okay? And I don't go into 5 dimensions because if you want to put explicitly the parameters, okay, which is what physicists do, I don't like, but because you A, at least for those purposes, okay? Then, so, what Cartanda is critical, so we saw equivalence problems. He obtains a set of differential work forms uniquely defined by the problem, and he differentiates them. And he keeps differentiating them until with the stereo derivative until he runs out of things to differentiate. You are going to say, how is that possible? In the second differentiation, you are going to get 0. What happens is that you differentiate one, okay, and then from that differentiation, you get new quantities which are the ones that you are going to differentiate. Example, if you do this is going to be of the form, as I explained the other day, some linear combination of animals like this, which these are not defined, there are millions of them that satisfy this equation. Because if I had one, I only have to add them some other terms, such as contracted terms, contracted with that gives Z. So, Cartanda shows in a page, there is another way of doing it, that that, because I mean, here we have a tensor structure. When we still differentiate, we have a different structure. So Cartan is working on two structures at the same time. Okay, one leg, each on different hops. And that is extremely difficult. It still can be done, but only the likes of Cartan can do it and be sure of what they are doing. Alright, so Cartan showed that one canonically obtains from this. For those of you who have taken general relativity, you have seen the form with other type of bases, not orthogonal bases, omega mu plus omega mu equal to u, which you have found under the statement that the covariant derivative of the metric is 0. This is exactly the same thing. Except that you see it in the context in which you have tangent vectors. Okay, and you differentiate in the thing of tangent vectors. But here, I don't have tangent vectors, at least, okay, at this level of representation. So this is the differential system that one has to solve. How do you solve this? What have you done in your relativity course?
So what are the known things and what are the unknown things?
What is nonsense and what is the nonsense?
No, the known things, if you say a system.
Yeah, the input is this.
This G.
And therefore this.
This.
And therefore here is the input and we have to find those.
Yes. Which are not uniquely defined.
They will become uniquely defined, not in which things of the omega mu which are dependent on bases, but in we were going to complete this.
But I do not understand the last code. Omega was not finished below.
Only because omega mu we lower indices.
Ah, you lower.
We come from another world, because for them that was trigger, right?
No.
Omega mu equals omega mu because the metric is technical. Okay? Because the metric is out, and here it is. The coefficients of the mu's are 0, and the coefficients of the mu's are 1. So the metric is 1, 0, 0, 0, 0, 0, 1, 0, 0, and with that metric we lower indices and just with total freedom. Okay, how do we solve this problem? First, for the benefit of, first under here, so the perspective. I am using on the normal basis. So I am going to write, or would be, this system this is the system, and below I am going to use, for the properties, so okay, I'm going to use omega mu equals omega mu. This case, these are all normal. I'm going to do here, area. And I'm going to do the here only. This is the one that unfortunately the physicists use. I do not mind using this because for normality it's a property which is canonical or Euclidean spaces, or without metric compatible affect connection. Which, if you read Cartan, he will tell you Euclidean rather than metric compatible affect. Which is a better language because Euclidean geometry is associated with Euclidean group, and affect geometry with affect group, and the numbers of parameters for the same dimension of the vector space is different from one place from the other. So by introducing metric incompatibility, you are forcing a relation which restricts the boundary of the geometry. Okay, so in general, ultimately, this would be the same. And this one would be omega mu mu plus omega mu mu equals g mu. Here, it is general, I don't have such a relation. Oh, yeah, I have two raised and lower with g. Okay, to raise and lower is g mu mu. Now, what is in coordinate basis? In coordinate basis, this is 0. And this simply gives you the components of that. We call them, Christopher, the gamma of three indices. That becomes this. This is terrible. This is terrible because when there is Thompson, okay, I mean, it is very difficult to see anything here related to the torsion. One side is that the torsion is the anti-symmetric part of the connection, but that is only true in certain cases. Okay, and now is the other one. The other one is the same. I mean, the same as this, not important. And this is the same side. How do you solve that for the omega mu mu? How do you solve for the Christopher series? You solve this system. You make 3 copies of this. You remember that? And then you use this here. Somewhat that then, and you get gamma mu mu lambda. Even in the simplest of the cases, this is a terminal way because you are dealing with 3 indices. Here, it is much easier because you only deal with 2 indices. And in addition, you have the anti-symmetry. So, you could, here, if you use the general, if you don't do it by inspection, which in general is very cheap, and I will do an example, then you will do the following. Instead of making 3 copies of the last one and using the first symmetry, you will make 3 copies of the top one and use the symmetry. And you will obtain the gamma mu. They are not these. Okay, it will be like components relative to different bases. With the added, okay, with the added inconvenience that this doesn't transform like a fusion. Therefore, in order to obtain the relationship between the gammas over here and the gammas over here, if I define them as by this, not only you have to have here a term where there are 3 partial derivatives of the system of coordinates with respect to the other, plus a non-linear term. Okay? You would have to deal with 3 indices, and that is so Cardano invented a method called inspection. It's trivial. It has a problem. It is inspection, and normally you inspect and to take the right result. But in principle, you have to check that. So you know how to solve this. I repeat, you make 3 copies of that, change the indices, play with indices. Use the symmetry, you have the sum, do the sum, and at the end, that's what comes out, the expression for the omega. But one minute, because even though color uses coordinate basis, yeah, he doesn't use inspection, and don't believe that just because your system is orthogonal or coordinates that things are going to be simple. They are not. You get unexpected result. Okay, so let me now solve this, do an example of this by inspection. I'm going to do which will be good to obtain divergences and colors, etc. on a spherical coordinate, with a spherical coordinate. R squared plus R squared d theta squared plus R squared sine squared theta d phi squared. I'm going to take the omega 1s in reality, the most general ones would have here, so we have to apply an orthogonal matrix, okay, to this column. But for this purpose, I don't need them because we wish to obtain our omega mu's as linear combinations. You say, why do you do that? Well, because automatically I do like that. Okay, because much simply we only can do it. For the moment, that's really enough. Alright. So, what is the value of what are we going to do? Compare with this. So we have the omega 1 equals 0. I'm not going to read. Inspection means that I'm going to see whether I can manage, okay, by, instead of I'm going to assume first that possibly this could be 0 and that could be 0 or maybe not. This could be proportional to omega 3, which is a bit. But when I'm going to get my information, instead of trying on possibilities, it's from the other ones, from that and from that, I'm going to start obtaining those. This is true, but it is not useful in using this method. And remember, if these were complicated, because it is not a diagram and things like that, then what you will do is brute force. You cannot do that. Okay, the omega 2. The omega 2 is dr theta. But we know that dr is omega 1. So if I use omega 1, I'm going to use 1 omega 2. And you're going to ask me, and why didn't you choose d theta? Okay, relate that omega 2 divided by r. I can do it, of course. Okay, but I didn't do that because now I have a blank video. Because my blank video is away, because you remember that this is over 40, omega 1, 2 plus omega 3, 1. So I have to identify this. Okay, get the omega 2 from, relate that by the omega 2, because I don't have the omega 2 here. Alright? And maybe you may have questions and say, why don't I have the omega 2 there? It has to do with this. You want to ask me later on, then we continue. So, I wrote, yes, the omega 2 is here is theta, so I'm going to write it as omega 1 because this is omega 1, omega 1, 2. Okay? Therefore, and this is all. Therefore, I compare this is going to be 0, which will not allow me to say that this is 0, but this allows me to say, aha, this is the number. Pardon me. This, if this is equal to v, that means that this is going to be 0, which does not imply that omega 3, 1 is 0. So, therefore, from the comparison, what was I doing? This is that. This is that. And that has to be done. Therefore, I read from here, this is omega 1. D theta, and from here, therefore, I read that. Correct me if I do something stupid, that is very likely. From there, I think that omega 1, 2 will be found by inspection. Therefore, omega, that is my first piece of information. So, I do the next one. The omega 3 equals dr sin theta by plus a differential in the second term. So it is going to be cosine theta dr d and I'm going to replace
and cosine theta.
the derivative of
No, the first is
r cosine theta d theta d phi. Simple. I said I was going to do something. I promised. Something stupid.
and the R.
Another error?
No, R. The letter R.
Huh?
The radius. Multiplying to cosine of.
Yeah. And here also.
No, this is not okay.
No, this one is for differentiating the R, right?
Yes.
Yeah, differentiating the R. This is from differentiating the theta, and here from, okay. So I will continue playing the game. And now you check. Because this has been, and we can make assumptions in there. Normally, this works. Check at the end. All right, so now I hope you have a little bit more experience with this. Perhaps what I should say is that we can say something else tomorrow. Now, can you
Time to go to lunch.
Oh, what time was it time for lunch? 1:30.
Half past 2 and we are.
Okay, lunch formally in the program is from 1:30?
Yes.
Okay, let's go. Lunch